Pick up again with approximation algorithms. If you recall, we were in the middle of talking about greedy algorithms. And I had just introduced you to the domain of scheduling theory. Where a problem is specified by a machine type followed by a set of constraints followed by an objective function. Okay. And there are scheduling problems involving one machine. There are scheduling problems involving parallel machines. There are scheduling problems using so-called related machines and unrelated machines. Do not ask me why they decided to use R for unrelated. Some things are just mysterious. We're going to be encountering various constraints later on. These include things like release dates or deadlines. And then there's the objective function. Two that we'll be looking at are Cmax, which is the max completion time. We'll also be looking at the sum of the CJs, which is the average completion time. But we got started last time with this particular problem, PCmax, where you've got parallel machines that are all the same, and you need to assign each job to one machine, and you want to minimize the time that the last job completes, which is, of course, just the total processing time assigned to that machine. We talked about a greedy algorithm, where we assign one job at a time to the least loaded machine. That is the machine with the least computation time on it so far. You know, I will mention, I'm going to talk about least loaded machines because, I mean, you can use this algorithm for completion time scheduling, but you can also use it for load balancing. If the jobs run forever, but each of them takes a certain amount of CPU or requires a certain amount of memory, then the same algorithm can be used to ensure that you're not using too much CPU or too much memory on any machine. Okay. Also, I'll just remind you, since we'll be using it a lot, that we always talk about having some number M of machines and N jobs. And the machines are indexed by I, and the jobs are indexed by J. Okay. So as we discussed last time, when you are solving when you're running an approximation algorithm, when you're trying to approximate something that's NP hard, and this, by the way, is NP hard. So we don't expect any exact solution in polynomial time because we don't think P equals NP. So anytime you're trying to run an approximation algorithm, in order to analyze its performance, you can't compare its performance to the optimum directly because you don't have the optimum and you don't know how to compute it. So instead, for a minimization problem like this one, you compare the performance of your algorithm to some lower bound, right? If your algorithm is using less than some alpha times the lower bound on what the opt does, then certainly the algorithm is also less than alpha times the value of the optimum, which is bigger than the lower bound, right? So we started talking about suitable lower bounds for our process when we're given our set of processing times PJ. Okay, so what lower bound did we have last time?
The average.
Right. So we know that one valid lower bound is the average processing time. sum of all the processing times divided by m, right? We know that that bound is less than or equal to the optimum because some machine has to use at least the average processing time. Okay. But we also observed that this is not always a good lower bound. Okay, so what is a case where this lower bound doesn't tell me very much?
When there's like very few jobs.
Yeah, and what's the fewest possible number of jobs where this would be a problem?
One.
One, right? So particularly bad is where you just have one huge job, right? Then your lower bound is off by a factor of m from the value of the optimum. And again, for the same reason as I was saying before that we use lower bounds, if the lower bound is off by a factor of m, you're not going to be able to prove, if your lower bound is a factor of m worse than the optimum, well, your algorithm is not going to do better than the optimum, which immediately says that you're going to be worse by a factor of m than the lower bound, right? So what we know is that the algorithm does at least as poorly as opt, which is at least m times the lower bound, which means that you can't prove an approximation factor better than m. Right? So that's a problem. So looks like this lower bound isn't going to work. Any suggestions for another lower bound that might help us deal with this kind of bad problem? Don't think too complicated. Let's look for simple lower bounds to start with. You always want to start there.
The length of the largest job.
Sure. Let's consider the longest job. Is this a lower bound? Sure. Right? You're going to have to put that job on some machine. And so the max completion time will be at least that much. Unfortunately, this lower bound is also bad. Right? What would be a situation where this gives us a terrible bound that's very far from the optimum?
Lots of jobs.
Yeah, tons of tiny jobs. Right? If I have these m machines and each of them is running, a tremendous number of tiny jobs of size epsilon, right? This is optimal, right? But the bound is going to have a ratio of at least 1 over epsilon times the opt, right? Or sorry, the optimum is going to be at least 1 over epsilon times the bound. And so again, the best approximation factor we can prove using this bound is 1 over epsilon, which actually can be driven to infinity. So this is even a worse lower bound than we had before. So now I've got these two lower bounds and neither of them works. So what could we do? Any thoughts?
Well, they both perform poorly in opposite situations. So perhaps you could just take the max of the two.
Good. So that's absolutely right. We've got these two lower bounds, but their problems are opposite. So if we put them together somehow, maybe they will cover each other. And that is indeed the case. And so, yes, you can think about the max, but mathematically, it's generally easier to think about a sum. Okay. So let's take a look at that. Okay. Let's consider the sum of these two lower bounds. Okay. Perhaps these will cover each other. Okay. So let's denote the average load by L. And let's consider the maximum job, I'll just use index J for that job. Okay. So let's think about what happens when we are building our solution greedily. Okay. So in particular, now let's consider the max load machine. The one that has the job that finishes last. Okay. From knowing that this is the maximum load machine, what can we say about it with respect to the way our algorithm behaves? Okay. And in particular, let's consider what happens when I add the last job, the one that takes it to the maximum load. Okay. What can I say about this machine with respect to our lower bounds when I add the last job?
All the other machines had to have larger workloads when you added the last job.
Exactly. That's the rule for where we add it. Now, if all the other machines have a larger load than this one, how can we relate the current load on this machine to our lower bounds?
So the total number, sum of the PJ is bounded by M times current load plus last job load.
Good. So let's take that one piece at a time, right? So, whoops, did you lose me again?
Yeah.
Yes.
That's so weird. My screen is still sharing just fine. Oh, but what's this? It looks like Zoom hung. Zoom crashed. That's never happened before. Oh, it's such a lovely day. I had to have my computer repaired this morning, and it's already blue screened once this afternoon. Let's see. Join. No, that's not what I want. Home meetings. Oh wow! It looks like now my pad may be having networking problems. No upcoming meetings. All right, hang on a minute. Everybody gets an unexpected break while I find the meeting ID. Okay, I'm back. Oops. All right, we have a screen again.
Yep.
All right. So when we add the last job, all the machines have larger loads. So what can I say about the load of this machine where I added the job? Well, I claim that this machine has a lower load than average. Everybody see that? Right? This is the least loaded machine at the time, right? And the total load is less than, the total load now is less than the total load that it will be, right? So the average load now is less than the average load that it will be. And my load is going to be less than, it's going to be at most the average. Yes? So now what happens when I add PJ? How can I relate this to the lower bounds?
Basically, it will be at most L plus PJ.
And right, so I get a load of at most LP plus PJ, but what can I say about PJ? How do I relate that to the lower bounds?
It's at most L on the lower bound since we have max job in there.
Exactly. So when I add PJ, it's less than or equal to L, right? So that means that my final load, right? Because this is the last machine, this is the last job that I added, is less than or equal to 2L. So, sorry, it's less than or equal to opt, right? And so that means that my final load is less than or equal to L plus opt, which is at most 2 opt. So I have a 2 approximation. Right. Now I can actually refine that just a little bit. Because essentially that last job that I'm adding it's not contributing to the average load that I assert for the first bound that I'm using, right? So when I add PJ to a machine with load, let's say L prime, okay, then the average load for the whole thing is at least L prime plus a 1 over m fraction of the job that I add. And this has got to be less than or equal to opt, because opt exceeds the average load. And so what that means is that we achieve this quantity L prime of the load that we had to begin with plus PJ, which is equal to L prime plus PJ over M plus PJ times 1 minus 1 over M. You see what I've done there? I've added PJ over M and subtracted PJ over M. Because now I can say that this first term is at most opt, but the second term now has a 1 minus 1 over m factor in it. So this is at most opt times 1 minus 1 over m. So in fact, the bound that I get is 2 minus 1 over m times opt. Okay. And so, you know, maybe not a big deal, but at least now if I have one machine, my result is tight, right? If I have one machine, then obviously I'm going to get an exact answer because there's only one answer. And also, if I only have 2 machines, I'm not going to be off by a factor of 2. I'm only going to be off by a factor of 3/2. Okay. Whoops. So any questions about this analysis? Nothing? Okay. I'll observe a couple things about it. One is that this algorithm is online. Okay. You can schedule as jobs arrive. I don't need to wait until I have all the jobs to produce the schedule. And that's why this is actually quite appealing for various load balancing applications. You can just go ahead with what you have and fill things in later. Okay. Another thing I'll mention is that this is tight. This 2 minus 1 over m result. That's another reason it's interesting versus 2. So can anybody think about how I would mess with this algorithm? Get it to do something that's really wrong? So if we think about how this algorithm, how we analyze this algorithm, right? The reason we ended up with 2 minus 1 over m is that we added the optimum. We added 2 copies of the optimum. We got 1 copy of the optimum from the average load and 1 copy of the optimum from the max load. So how might we feed jobs to the algorithm one at a time so that it ends up actually doing that, sort of building up something which is pretty much the average load and then sticking a max load on top of it in order to generate twice the optimum.
We can start with a bunch of small jobs until so it's like pretty balanced until the very end where we have a job that's just as big as the load on that machine combined.
Exactly. So what we'll do is we'll put in tons of tiny jobs. Roughly m over epsilon jobs of size epsilon. And then one big job of size 1. Okay, so the problem is that the algorithm will put, whoops, jeez. The algorithm will take all of these machines that we give it, and it will spread the jobs evenly over all of the machines because it keeps on putting the tiny job on the least loaded machine. And then at the end, we'll come in and we'll give it one big job. Okay. And this is not even close to optimum, right? This is off by 2 minus 1 over m. What should we have done to get an optimum schedule?
Do the big job first and then do greedy.
Yeah, so that's actually kind of an attractive way to tackle it, right? So the problem was that we just ran ahead and scheduled the small jobs and we didn't leave space for a big job. Right? What we should have done was made one job, left one big hole for the big job and scheduled the small jobs on all of the other machines. Okay, so that's why we're off by a factor of 2. And as was suggested, we could get around this by scheduling the longest jobs first. Okay, and this is known as the longest processing time heuristic. Or LPT. And you can prove that this actually achieves a 4/3 approximation. Okay. I've never put that on the homework, but maybe I should. It's kind of not too bad. It does have the drawback of being not online. You need all the jobs at once in order to know which are the longest jobs so that you know which one to schedule first. Okay. Okay. So now we've seen these nice greedy algorithms and shown that we're able to achieve a variety of approximation factors. We had some 2 approximations, a log n approximation. I'm now going to start talking about approximation schemes. Which are really driven by the question of how good can we get? Right? All we know is that there's no one approximation, right? We can't get exactly the solution. But can we get really close? Maybe, I just told you there's a 4/3 approximation, but maybe there's a 100 over 99 approximation or a 1,000 over 999 approximation. Okay. Now, of course, if we're going to ask that question about what's best, it also raises the question of how we could possibly prove that it's best. Okay. So I'm going to mention at least these 2 concepts. On the one hand, we're going to talk about approximation hardness. So using various techniques from complexity theory, the same sort of stuff that's used to prove NP completeness, we know that there are some problems that have a lower bound greater than or equal to 1 on their approximation ratio. So unless P equals NP. All right, so some problems cannot be approximated to within a factor better than 2, or a factor better than 8/7, or a factor better than 0.878, 1 over 0.878. We're not going to look at those hard problems for a moment, for now. Instead, I'm actually going to talk about an approximation scheme. Okay, so an approximation scheme for a problem is a whole family of algorithms. A sub epsilon, such that A sub epsilon is a 1 plus epsilon approximation algorithm that runs in polynomial time. Okay. So basically, there are some problems where you can get as close as you want to the optimum solution. Okay. But you can never actually get there. Okay. Now, if you think about it, if I have a whole collection of algorithms, I can ask about, it's kind of a, I call it an approximation scheme, but I can really also think of it equivalently as an algorithm that takes the input and epsilon and runs in polynomial time. Okay, but we have to be a little bit careful about this because, for example, what if I have a running time of n to the 1 over epsilon squared? Okay, and I'm not pulling this out of a hat. I actually have developed approximation schemes with this runtime. Okay. And the point is that this is polynomial time for any epsilon, or for each epsilon. Right? But despite the fact that it's polynomial time for each epsilon, it's not an algorithm that you would really want to use for every epsilon. The problem is that it's not polynomial in epsilon. Okay. So we add this even more powerful or more demanding concept of a fully polynomial approximation scheme. Otherwise known as an FPAS, which is one where the runtime is polynomial in n and in 1 over epsilon. Okay. So do people understand this idea of an approximation scheme and the difference between approximation schemes in general and fully polynomial approximation schemes? Good. So we're going to spend the rest of this lecture exploring both of these concepts. So I'm actually going to start by looking at fully polynomial approximation schemes, which are the more powerful, but in some ways are actually easier. They're often easier to think about and easier to develop. And I'm also going to show you a tie between these fully polynomial approximation schemes and pseudo-polynomial algorithms. So you remember we encountered these pseudo-polynomial algorithms in the context of max flow. These were algorithms whose running time was polynomial in the value of the flow, right? Or polynomial in the largest capacity. And that's technically not polynomial because those large numbers, like the largest capacity, can be written down using a logarithmic number of bits. And so being polynomial in the numbers does not make you polynomial in the input size. However, with NP-hard problems, right, we already know that we're not going to be polynomial in the input size. And so this is another kind of polynomiality that we can hope to achieve and that we sometimes can achieve for NP-hard problems. So in order to demonstrate this, I'm going to go back to the knapsack problem. Okay, you'll recall that the idea here is that we have profits Pj for each item and sizes Sj, right? And we're asking for the maximum profit achievable given some size constraint. Which I will denote by S, I guess. Okay. And I'm now going to assume, in order to derive a pseudo-polynomial algorithm, that the profits, that the sizes are integers. Okay, so that this lets me do things involving the sizes that I can't necessarily do with arbitrary numbers. And in particular, it's going to let me invoke the paradigm of dynamic programming. Okay, so what I'm going to do is I'm going to define this recursive quantity. I'm going to say that B of JP is the smallest in size set from items 1 through J that achieves profit P. Okay. So if I am able to compute the smallest size item that achieves a certain profit, can I answer the question of what is the maximum profit achievable given a certain size bound? Right, so in particular, B of NP for any particular value P, oh, sorry, I misspoke. It's not, I'm not going to assume integer sizes. I'm going to assume integer profits. You're going to assume integer sizes in your homework, but we're going to work with profits. So if I define B of JP to be the smallest size subset of 1 through J that achieves profit P, then B of NP is just going to be the smallest subset achieving of all the items achieving profit P. So if I'm able to compute that for every P, I claim that gives me the answer to my question. Why is that?
Basically,
So if I know the smallest size collection that achieves every possible profit, how do I decide what the max profit achievable is for a given size?
you can just do a linear scan, basically stopping when you go over that size limit. Overall profits.
That's right. I mean, I don't even have to do a linear scan because these things are going to be ordered, right? So clearly the profits increase with size. Right? Or sorry, let me put it the other way around. The sizes increase with the profits. So once I have this list of all attainable profits for every size, I can just search for the largest profit achievable with size less than or equal to S. Right, and actually a binary search will be sufficient here. Okay, so now that I know that answering this question is sufficient, let's look at how I can answer this question, right? I am going to use dynamic programming, which means that I need to show that it's possible to figure out an entry of this dynamic programming table by reference to smaller entries in the dynamic programming table, right? So give me some sort of recursive formulation that tells me how do I make the smallest possible subset of 1 through j plus 1 items that are of the items numbered 1 through j plus 1 that achieves profit P.
We can either include the last item or not. So
Exactly.
it's
Right.
like
There's just this one binary choice to be made. Yeah, min. So we have two choices, right? Either we include the last item or we don't, item j plus 1, or we don't include item j plus 1. So if we don't include item j plus 1, what profit can we achieve? Or sorry, what size, if we don't include j plus 1, what will the optimum size be?
BJP.
Exactly, right? We're not including, right? The point is that any subset, right? The optimum subset that does not include item j plus 1, the smallest subset that achieves a profit P without including j plus 1, well, that's just a subset of 1 through j, so it's the smallest subset that includes items from 1 through j to achieve that profit P, right? What's the other possibility? The other possibility is that we do include item j plus 1. So what does that tell us about the size of the optimum in that case?
It's like SJ, or the size of the item j plus 1, and then plus BJP minus the price of item j plus 1.
Profit. I know why you said price, because that's what we've been doing, but now P's are profits, right? So the point is we take the j plus 1 item, and we also, in order to achieve profit, the right amount of profit, we need to get the rest of the profit from the items 1 through j. So we take our target profit P, but we've already achieved profit PJ plus 1. So we need this much more. Okay. So I want everybody to look at this and make sure they believe this recurrence, right? That to get the optimum profit for the first j plus 1 items to achieve profit P, the minimum size of that involves looking at what size you need to achieve profit P from the first j items, and also what size you need to achieve profit P minus PJ plus 1 from the first items, and then from the first j items, and then you just put those two things together in order to give you the optimum for this subset. Any questions about that? So now it should be pretty clear that we can put this inside of a loop, right? Where we go from 0 to n, and then we go from a profit of 0 to a profit of whatever the maximum achievable profit is. And we fill out the table in that order, right? So we don't actually run this as a recurrence. that would take exponential time, but instead we just iterate over all of the table entries in order to fill them in. And the point is that by the time we're trying to fill in the J plus first row, we have the Jth row complete. And so we have all the information we need in order to fill in the J plus first row. Any questions about this? So what's its runtime?
O of n times the sum of the prices.
Exactly. Right? And of course, there are only n prices, right? So I can rewrite this as O of n squared times the maximum profit, or sorry, now you've got me doing it. N squared times the maximum profit. Yes? If you think about it, I can actually here stop at the optimum profit, right? I'll let you fill in the details, but basically I can binary search on what that optimum profit is. And I can kind of terminate the dynamic program when it gets bigger than that because it's not relevant to my problem. All right, so it's actually n times the optimum price. Okay. So now we have a polynomial time algorithm for knapsack. Or do we? Well, as we've discussed, this is actually a pseudo polynomial time algorithm for knapsack. Okay. And so this does not violate P equal NP because this runtime is not polynomial in the input size, but it is polynomial in the numbers that show up in the input. Okay. But I do want to emphasize that this is not even weakly polynomial. Okay. Now, we've given this approximation algorithm. This actually proves something about knapsack or calls for an important definition. What we've shown is that, well, knapsack is NP hard, but not with regard to its numbers. So what we say is that knapsack is only weakly NP hard. Okay. There are some problems that are strongly NP hard. And what that means is that there is no polynomial time algorithm even if the numbers are small. Okay. So here we have right? So what we've shown is that knapsack is that it is polynomial time if the numbers are small. Right? If all the numbers are polynomial in n, then in fact the runtime of the algorithm is also polynomial in n. But that's not true of some other problems. Can anybody think of an example of a strongly NP hard problem among the ones we've already seen? Well, it's kind of a trick question, but if you think about it, vertex cover is strongly NP hard, right? Why is vertex cover strongly NP hard? Because it doesn't have any numbers in it, right? And so it doesn't matter if the numbers are big or small because they aren't there, right? But there are some other problems that we'll see later, which are strongly NP hard, even though they also involve numeric values. Okay. All right, so this is nice that we have this pseudo polynomial algorithm, but we're looking for polynomial algorithms, right? So now the question is, given this pseudo polynomial algorithm, what can we do about finding a fully polynomial approximation scheme? So the problem is, what do we do if the profits, what do we do if the profits are large? We can't afford to run our pseudo polynomial algorithm with large profits. So what should we do? If we've got big numbers and we only have an algorithm that works for small numbers, what might we try?
Scale the numbers down, like the profits down?
Yeah, let's just shrink the numbers. Okay. So in that case, we are going to need to do some rounding because we have to keep things integer for our pseudo polynomial algorithm. Okay, so let's suppose that our optimum is some number p. And I'm gonna have to come back, I don't know what p is, so I'm gonna have to come back and address that supposition, but let's suppose for now that we know p. So what we can do is scale all the profits. What I'm gonna do is I'm going to shrink them down so that they are polynomial size, okay, in n over epsilon. Whoops, didn't need those parentheses, sorry. Okay, but now I'm also going to scale down by this big profit P. Okay, so I'm going to multiply each profit by a scaling factor, and then I'm going to round down. Okay. So if I perform this transformation, what can I say about the new profit of the old optimum? Right, notice I've changed profits, but I still have the same items. So if I just look at the new profit of the old optimum, what's it going to be?
Floor of n over epsilon.
Sorry? Yeah, it's going to be about n over epsilon, right? Because roughly speaking, we're going to take the sum over the optimum of these quantities n over epsilon p times pj, right? Now, rounding down like that subtracts only the fractional part. So this is going to be at least the sum over these optimum values of n over epsilon p times pj minus 1. Yes? But now I can pull out the whole scaling factor and get back the sum over the optimum of the pj's. And then I also have to sum over this optimum some 1s. So how do I simplify this?
Well, the sum of the pj's is equal to p.
Exactly. So this is just equal to n over epsilon, right? The p in the denominator cancels the sum of pj's. What about the second term?
Can we say that it's at most n?
Exactly. So we have something that is at least n over epsilon minus n. And this is why I introduced this epsilon, is that the subtraction of n is not a big deal, right? It's only a small piece of n over epsilon, right? Now, I've just looked at the new profit of the old opt, right? But that means that the new opt, right? The new optimum might be a different set, but its value is going to be at least this quantity because there is a solution whose value is this large. Yes? So that means, but now we can also see that the largest PJ, right, is at most, this scaled quantity, n over epsilon p times pj, which is less than or equal to n over epsilon, okay, which is a polynomial number. So we can use the pseudo polynomial algorithm to find it. Okay. And if you go back to our analysis of the runtime of the pseudo polynomial algorithm, it's n times p opt, which in this case is n squared over epsilon. Okay. So now we have found a solution with these scaled profits. What can we say about that solution with regard to the original problem? So we can now return to original values, right? We have a set of items. Right? So what can we say about the value of the set of items that we just found? Well, what happens to a profit when we unround it? How does it change its value? Well, we multiplied and rounded down. So for unrounding, we're going to make it a little bigger, right? Pj plus a fraction. And then we're going to multiply it by epsilon p over n. Yes? And so that means that our overall profit is at least the scaled profit of n over epsilon minus n times the scaled profit of epsilon p over n. Right? And now the n's cancel, and we just get 1 minus epsilon times the optimum profit. Any questions? Right? What I've shown is that regardless of the value of the profits to start with, by scaling and rounding and applying our pseudo polynomial algorithm, we can find in n squared over epsilon time a 1 minus epsilon times optimum solution, right? So this is a 1 minus epsilon approximation in order n squared over epsilon time. And so that fits the definition of a fully polynomial approximation scheme.
What's the value p we are dividing by?
That's the value of the actual optimum, right?
Uh-huh. How can we just divide by that in the algorithm?
Ah, yes. So you are remembering that I flagged this, right? I said, suppose that the optimum is p, right? But now we have to justify this supposition, right? Say, wait, how do we know p? Right? Well, you notice that I don't actually need p, right? Really, all I need is an upper bound on p. Sorry, a lower bound on p. Right, so I know that p is bigger than the largest profit, right? And that means that scaling and rounding reduces this profit to n over epsilon times the maximum PI instead of P opt, right? Times P, or times, and we also have this upper bound on the profit, right? So here we have a lower bound because we're putting it in the denominator. And here we put an upper bound because it's in the numerator, right? So this gives me overall an upper bound on the new profit, which is n over epsilon times the sum of profits divided by the maximum profit. But the sum divided by the maximum is at most n. So the value of the profit here is going to be at most n squared over epsilon, right? Remember that if we knew the optimum, we would get a profit value of n over epsilon. Now the value of profit that we get is a little bigger. It's n squared over epsilon, but it's still polynomial. So we can still use the pseudo-polynomial algorithm. And that the runtime will now increase to order n cubed over epsilon. Does that make sense? So we don't actually have to work with the optimum profit. We just have to work with an upper bound on the optimum profit. And we've got one that was close and a lower bound on the optimum profit. And since they're close enough, we can use those instead of the exact profit. Any questions about that? If not, I want to show you a slightly faster method, okay, which is guessing, okay. Suppose we try and guess some value of P and try to run the algorithm, okay. So what might happen? Let me break this down by cases, okay? So suppose first that our guess is bigger than P, the optimum, our guess P, let me use P for the guess, is bigger than the optimum by a significant amount. Okay. So what happens when we run our algorithm? Well, the optimum solution scales when we use this P to a solution of value n over epsilon P times opt minus n, right? We already sort of saw that. But now P is like opt over 1 minus epsilon. So this turns into a value of n times 1 minus epsilon. This turns out to be bigger than n over epsilon minus n. Okay. And what that means is, sorry, did I do this backwards? Hang on just a minute. Right, sorry, I put things backwards, that's the problem. So the problem is that we're dividing something by something that's bigger than opt by quite a bit. So opt gets scaled down by something that is too much. And we end up with an optimum that is less than n over epsilon minus n. Right? We used a guess that's bigger than the optimum. And so the true optimum scales too far down to something that's smaller than n over epsilon minus n. So our pseudo-polynomial algorithm will not find a solution of value n over epsilon minus n. Remember, that's what we were looking for in our pseudo-polynomial algorithm, so that it would scale up to the proper value, right? And so this will tell us that our guess was too big. Okay. On the other hand, if I guess a p, which is less than the optimum, right, then opt will scale to at least n over epsilon minus n. So a solution of this value will exist. Now, if I guess too small, there might be even better solutions. And I won't find them because I stopped looking at n over epsilon minus n. But I will find a solution of sufficient value to tell me that my guess was small enough. All right, so if I guess too big by a significant factor, I find out I'm too big. If I guess too small, then I find out that I'm too small. And so this is sufficient to let me do binary search. Right, I keep trying different values of p until I get close enough to the optimum to find a solution of the size that I'm expecting. Okay, and this lets me solve the problem with order log n or so trials. Actually, let me not fill that in yet. So you can see how I'm going to do binary search, but I do need starting values, right? Starting lower and upper bounds. So can somebody tell me what is an obvious lower bound and upper bound for this binary search that I'm going to look for? Like, what is definitely smaller than opt and what is definitely bigger than opt?
0 and the sum of all PIs.
Okay, so for the upper, we can definitely take the sum of the PIs because that's the biggest set I can take. The lower bound of 2, that's true, but it's a little weaker than I want. Actually, 2 is not even a lower bound because the PIs might all be small fractions. So what can I do for a lower bound?
The minimum PI.
Yes, but I want a strong lower bound, so instead I'm going to take the maximum PI that fits, right? If there are some items that don't fit in the knapsack at all, I can just drop them from the problem. But I have this maximum PI and the upper PI, and notice, as we discussed before, that the ratio of these two things, the sum divided by the maximum, is at most n, right? So the ratio between my upper and lower bounds is at most n. And so in fact, what this suggests that I do is try the min and 1 plus epsilon times the min and 1 plus epsilon squared times the min and so on until I get to the max. Okay, and one of these will be close enough for the algorithm to work. Okay, and the number of tries is just going to be, you know, how many powers of 1 plus epsilon are in this ratio between the maximum and the minimum, which we've already argued is at most n. Okay, and that's log n over log 1 plus epsilon. log 1 plus epsilon is about epsilon. So you only need about 1 over epsilon log n trials to home in on the proper value. In fact, if you just want to get a little crazy, instead of trying all of them, you can binary search among them. Right? And that means you only need log of 1 over epsilon log n trials, right? So log n plus the log of 1 over epsilon. So the dependence of this algorithm on epsilon is tiny, right? You can go right ahead and, you know, set epsilon equal to 1% or 0.1%. And your algorithm will still be extremely fast. So even though knapsack is NP hard, we can get as close as we want with essentially a linear time algorithm. Or sorry, quadratic time algorithm. Okay? Any questions about this? All right.
Question.
Sorry. Yes.
How much work? First the iPad dropped down, and how much work do we need to do in each step of the binary search?
We need to run the pseudo polynomial algorithm, right? So the point, I'm working on the iPad, but each step of the pseudo polynomial algorithm is going to tell you, sorry, each step of the binary search, you run the pseudo polynomial algorithm to find out if you get a solution of the size you expect, right? And so that's the, so that log 1 over epsilon log n is, sorry, you still don't have it, right?
No.
Zoom is hanging. Oh, here we go. Connecting. This must be a Wi-Fi problem, which is kind of silly since they're both on the same network. Still nothing? Let's see. Share content screen, start broadcast. There we go. Back. All right. So sorry, I don't know how long the screen was lost, but essentially, the number of we need to perform a search over possible values of the optimum. We don't need to get the exact value of the optimum. We just need to get within a 1 plus epsilon factor of the optimum, because we're only looking for a 1 plus epsilon approximation anyway. And each step, we try one execution of the pseudo polynomial algorithm. Okay. Now, this technique that I used, right, took a pseudo polynomial algorithm and turned it into a fully polynomial approximation scheme. And it's very general purpose, right? All we did was round off the numbers and run the pseudo polynomial algorithm. So basically, any pseudo polynomial algorithm that you have for an NP hard problem can be used to produce a fully polynomial approximation scheme for the same problem. Okay. And it actually goes the other way as well. Okay. If I have a fully polynomial approximation scheme, I can create a pseudo polynomial algorithm for the problem. Okay. So how do I do that? Well, suppose the input to a problem uses integers bounded by some t. So that when you combine them, n items, so that when you combine them over whatever feasibility space there is, your optimum is at most n times t. Okay. Now, if I tell you that I have a fully polynomial approximation scheme for this problem, I can approximate to within any epsilon I like. I claim I can use that to exactly solve this problem. How do I do that? Remember, a pseudo-polynomial algorithm, you specify your epsilon, and it runs in polynomial time. So what epsilon can I specify here?
One over nt.
Exactly. I'm going to make it a little bit bigger just to avoid any fear of edge effects. I'll take 1 over 1 plus nt, okay, to be epsilon. Okay, and so now I find a solution of value at least, or rather my FPAS will find a solution of value at least nt divided by nt times 1 minus epsilon, right? Which is nt minus nt over 1 plus nt, which is greater than nt minus 1 and is therefore equal to nt. Okay, so if I set the epsilon really small, I get back an optimum solution, and my runtime is now polynomial in the input size and also the value of the solution, but that's just polynomial in n and t. Okay, so very straightforward to transform from a fully polynomial approximation scheme to a pseudo-polynomial algorithm. They're essentially the same thing in slightly different disguises. Any questions? All right, so this basically creates an equivalence that essentially there are these weakly NP hard problems. And they have fully polynomial approximation schemes in general. Okay, and you can actually turn this into a complexity theory statement. There's a paper about that I can point you out if you're interested. Okay. So now all we have left is all the not weakly weakly NP hard problems. What do we do about those? So for that, I'm going to introduce you to another general purpose technique, which is called enumeration, and which is basically a kind of controlled brute force. Right? So we know that we can solve just about any combinatorial optimization by brute force enumeration of all the answers. Right? If we look at all the answers, we can find the best one. The problem is that looking at all of the answers is too expensive. So we need to find ways to reduce the answer space so that we can afford to look at all the possibilities. And we want to do that reduction in a way that preserves the optimum somehow. Okay. So let's go back to PC Max. Okay. And imagine, like, we already saw back in when we were looking at this, I showed you an example of, like, you know, if you feed in a whole pile of small jobs and some big jobs, right? The small jobs just kind of naturally spread themselves out, right? They don't cause any problems. The real problem is the big jobs, which might end up stacking in the wrong place. So this suggests an approach to solving PC Max. What I'm going to do is I'm going to schedule the largest k jobs optimally by brute force. And then once the large jobs are out of the way, I'll just greedy the remainder using Graham's rule. Okay. So let's talk about the performance of this algorithm. Okay, so what can I say about the value of my solution? Well, if I'm first scheduling the largest k jobs optimally, then when I'm done, I'm going to have something that's optimal, right? And now I take that optimum solution and I start piling on all the smaller jobs. So how bad can things get? Right? If we think about our analysis of Graham's rule, right? How do we analyze the way that our algorithm diverged from optimum? Well, we sort of said when we add a job, we're adding it to the least loaded machine, right? And so whichever machine ends up with the maximum load, it's going to happen because we added a job to it when it had the minimum load, right? And so the sort of error that can introduce, right? We know that its load before we added was below average. And so at worst, we take the average load and we add a job to it, right? So the Graham part adds one job to a machine with below average load, which means that it's less than or equal to the optimum, right? So that means that each time I add a job, right, its completion, that machine has completion time at most the optimum plus the time of the job that I added, right? So let's consider the machine with the worst CJ, the worst completion time. Okay. There's two cases, right? If this CJ is caused by one of the k largest jobs, then what can we say about our solution? Right? If the thing that determines the runtime of our solution is one of the k largest jobs, then what can we say about the runtime of our solution? I'm sorry, I mean the scheduled time, not the execution time of our algorithm.
This is an exact algorithm.
Yeah, in that case, we are optimal, right? Because we ran an optimal algorithm and that still is what is determining the size of our solution. So we must still be optimum, right? If it's caused by a smaller job, right? Then its value, then our max completion time is at most the optimum time plus the added job, right? But the key here is that this added job is not one of the k largest jobs because we didn't run those greedily. Okay. So if I call this job pk plus 1, right? If I assume the jobs are ordered, right? Then what I know is that my maximum is at most this optimum plus this k plus first job size. Okay. But now notice that the optimum value, I know that I have k jobs that are bigger than pk plus 1, right? So my total processing time is at least k times this job length. And so the average processing time is at least that divided by n. Okay. People agree with this? And so that tells me that pk plus 1 is at most m over k times opt. And that in turn tells me that my solution is at most the optimum plus m over k times the optimum, which is 1 plus m over k times the optimum. Okay. And so what this tells me is that if m is fixed, I can always choose a bigger k and make my approximation algorithm as close as I want, right? Now, what's the runtime of this algorithm? Well, I have to try all solutions for k items being assigned to m machines. Right, in order to find the optimum for the k biggest jobs. And the runtime for that is going to be roughly m to the k. Because for each of the k jobs, I have to try m different possibilities for where it goes. Okay. So if m is a constant, it's m over mk times n for Graham's rule following. Or sorry, plus n for Graham's rule following. Okay. So if m is a fixed constant, this is polynomial time for any k. And that means, and it's also, so what this means is that I can get arbitrarily close to the optimum while staying polynomial in my runtime. And so this gives me a polynomial approximation scheme. Now, do people see why it's not fully polynomial?
It's not polynomial in so epsilon here is like around 1 over k, and it's not polynomial in that.
Exactly. My epsilon here is m over k. So the runtime of my algorithm is actually m to the m over epsilon runtime. So it's not polynomial in epsilon or in 1 over epsilon. Okay. And it also requires that m be a fixed constant. Okay. Because otherwise you have, right, if m is large, then you also have to make k really large in order to achieve a small epsilon, and then your runtime isn't polynomial at all. So this is not satisfactory. And so next time, I will show you how to generalize this idea to give you a polynomial approximation scheme that works for all m. All right, and we'll pick that up on Friday. Any final questions? Okay. I didn't get a lot of questions today about how things worked, which actually makes me nervous because I fear that it may mean that people are lost. So I will remind you that if you are lost, you should ask questions because I am very happy to take them and then you won't be lost. Okay. The other possibility is this is incredibly easy. I don't think so, but you know, if I'm going too slow, let me know by email. I can always speed up the class. Okay. Great. Thanks, everybody. TAs, if you can stick around for a short staff meeting. Everybody else, I'll see you on Friday.
Thank you.